In this segment, we'll talk about higher order ordinary differential equations, and we'll look at an example and we'll solve it by using Euler's method. So here we have an example which is given to us, a second order differential equation, and we're asked to use a step size of 0.25 to estimate the value of the dependent variable y at 0.5. We're also asked to calculate the absolute relative true error when the true exact value is given to us. We're also asked to find the slope of the dependent variable y with respect to time t at t equal to 0.5. So let's go ahead and see how we can go ahead and solve this problem by using Euler's method and taking the second order differential equation. So let's go and see that how we can go ahead and take the second order differential equation and reduce it to two first order differential equations, because before we do anything else, we got to be able to do that in order to apply the numerical methods of solving ordinary differential equations. So I'm going to introduce a variable called z. So dy by dt will equal to z, which simply implies that the second derivative of y with respect to t will be given by dz by dt, and this is what's going to help us to reduce the second order differential equation to simultaneous first order differential equations. So if I substitute these two quantities into here, what's going to happen is that I'll get dz by dt here, then 2 instead of dy by dt I'm going to put z plus y equal to e to the power minus t. And if I rewrite this, I'll get dz by dt is equal to e to the power minus t minus 2z minus y. And the reason why we're doing this is because we want to write in the form which will allow us to write it as a first order ordinary differential equation with the dependent variable with respect to the independent variable, and consider that to be the slope, will be the slope of z with respect to t. So having said this, what we have now is that we have dy by dt equal to z, and that is our first function f1 of t comma y comma z, and the corresponding initial condition will be on y, so it will be y sub 0 equal to 1. Then we have dz by dt, which we just calculated here, is e to the power minus t minus 2z minus y. It will be another function, let's call it f2 of t, y, and z, and z sub 0 will be equal to 2, because what is z? Z is dy by dt, so z of 0 is equal to 2. So we have first order ordinary differential equation, a second first order ordinary differential equation, and we'll be solving these simultaneously in order to be able to find our y at 0.5, which is part A of the problem. So let's look at this. We have dy by dt equal to z, which is our function f1 of t comma y comma z, and then we have dz by dt equal to e to the power minus t minus 2z minus y, and that's our function f2 t comma y comma z, and of course we have the initial conditions attached to it. So if we choose I equal to 0, what that's going to tell us that, hey, t naught is equal to 0, because that's what the initial condition is given, that our y naught is equal to 1, and our z naught is equal to 2, because those are the initial conditions. From there, if I apply the Euler's method, y sub I plus 1 is equal to y sub I plus f1 t I comma y sub I comma z sub I times h. So that means that y1 will be equal to y naught plus f1 at t naught comma y naught comma z naught comma h. Very important to carry all these steps, not only to avoid any mistakes, but also to understand how the procedure works. So we know y naught is 1, and the arguments will be 0, 1, and 2 based on these values, as times h, which is 0.25. Now, what is the value of the function f1 at these values of t, y, and z? Since it is just z, it will be just this value 2, so it will be 2 times 0.25, and we get that value as 1.5, and that's the approximately of y at 0.25 because that's y1. So once we have said that, let's go and calculate z1. So we now want to find z1. So let's go and rewrite our, not rewrite, but write our equation for Euler's method. So if we are given what dz by dt is z sub I plus 1 equals z sub I plus the function f2 at t sub I, comma y sub I, comma z sub I times h. And we know that, hey, at I equal to 0, we're still at this particular node. Then we get z1 is equal to z naught plus the value of the function f2 at t naught, comma y naught, comma z naught times h. And z naught is 2. The arguments are 0, 1, and 2 here because t naught is 0, y naught is 1, z naught is 2, and h, of course, is 0.25. Now we know what f2 is. F2 is given by e to the power minus t, which will be e to the power minus 0, minus 2z, which is 2 times 2 then, and minus z1, which is, minus y, which is 1, and times 0.25. So that's just coming from the expression for f2. And if you solve this, you're going to get 1. So this is the approximate value of z at 0.25, which is same as the value of dy by dt at 0.25, because that's how we have defined what the z variable is. But we are still not done, because if you look at the way it goes, it's from 0. We take the first step size, we get to 0.25. We'll take one more step in order to be able to get to 0.5, so that we can answer the question, hey, what is y at 0.5 equal to? So let's go and do that. So again, what we have is y sub I plus 1 is equal to y sub I plus the value of the function f1 at ti, comma y sub I, comma z sub I times h. Now we're going to choose I equal to 1. So that means that we get y2 value from knowing what is happening at t1, y1, and z1. And y1 is, which we just found out to be how much? We found y1 to be 1.5. And then we have the value of the function. Let's see what t1 is. T1 is 0.25. y1 we just found is 1.5, and z1 we just found out to be how much? We found out to be 1. And then we have 0.25 as the value of h. So having said that, we have 1.5. What is f1? F1 is nothing but z, so that will be just this value 1 times 0.25, and that gives us 1.75. This is the approximate value of y at t2, right? And what is t2? T2 is nothing but 0.5. So if you are going to look at this is t naught, this is t1, and this is t2, this is 0, this is 0.25, and this is 0.5. That's how we can look at it, because we're taking a step size of 0.25. And that takes care of part A. So our part A answer is that, hey, y at 0.5 is approximately equal to 1.75. Part B is asking us, hey, what is the absolute relative approximate error, which is given by exact value minus approximate value divided by exact value, and if you calculate in terms of percentage, it's multiplied by 100. The exact value is already given to us. It is given as 1.592. The approximate value we just found out to be 1.75, and we divided by the exact value, which is 1.592 times 100. Many people ask me, how do you find the exact value? You can just apply your ordinary differential equations course, like Laplace transforms, or the classical solution technique of finding homogeneous and particular part of solution to be able to solve the problem. But anyway, so what we get is 9.92% is the absolute relative approximate relative true error for this particular problem. So in part C, what we're asked to do is to find the value of dy by dt at 0.5. But we know that dy by dt is z, so basically what we're asked to find is the value of z at 0.5. So go back to our Euler's method formula, which is z sub I plus 1 is equal to z sub I plus the value of the function f2 at ti comma y sub I comma z sub I times h, right? And here we're going to choose I equal to 1 again because we are interested in finding z2, because z2 is the value of the function z at 0.5. So we get z2 is equal to z1 plus f2 at t1 comma y1 comma z1 times h. And what is the value of z1? Z1 is nothing but 1, which we found out from the first step. And let's see what is f2. F2 t1 is 0.25, y1 is 1.5, z1 is 1, and times h, which is 0.25. So we have 1 plus, what is the value of the function f2 at these values of t, y, and z? We just look at f2, it's e to the power minus t, so it will be e to the power minus 0.25, minus 2 times z, which is 1, minus y, which is 1.5, times 0.25. So if we find this value, we get 0.3197. And that is the approximate value of z at 0.5. And that is what we are in fact looking for. And that's the end of this segment.